In this lecture, we will confine our discussion to the initialization and readout of quantum dot qubits. When we discuss quantum dot qubits, there are two kinds of architecture. The original idea of using quantum dots to host qubits was by Loss and diVincenzo, came out in late 90s, where you can use the spin states of single electrons confined in a single dot to store and manipulate information. So, in the absence of any field, the state, the potential would look somewhat close to a parabola in shape of one dot. That would split into two spin states, up and down, under the application of a magnetic field. One you can assign as 0, another one is 1. And you can drive transition between these two states by applying electromagnetic radiations of energy equal to splitting, which is G mu B in B, where G is the G factor, mu B is the Bohr magnitude and B is the field. So, this is a field tunable energy splitting. So, you have the freedom to choose the energy splitting of the qubit states. And this is also different for material with a different G factor, and even the up and down states can flip depending on sign of the G factor too. For example, silicon has a G factor of +2, whereas gallium arsenide, another popular system, has a G factor of -0.44. So, what that means is, for a system of silicon, we will have a larger splitting, or you can get a appreciable splitting at a lower field. Okay. There is a 4 times approximately, the G factor is 4 times lower for gallium arsenide. So, you need 4 times larger field to get the same splitting compared to that of silicon. And this architecture of using single electron spin state in single dot is called LD qubit or Loss diVincenzo qubit. Now, there is another approach, there is a parallel approach that is called singlet-triplet qubit. Just to understand that, we need to understand what are the singlet-triplet states in this system. Now, we are talking about not one dot, you have 2 dots, each has 1 electron. When you couple these two together, then you get a energy splitting, which you can call bonding and anti-bonding orbitals. The splitting will be more when you have the low coupling, and splitting will be high when you have large coupling. When they are far apart, that means low coupling, they are similar state. When you bring it closer, and eventually the coupling is, they will split more, they will anti-crossing. It's an anti-crossing. Okay. Now, these states, there is a singlet state and there is a triplet state. The triplet state means there are 3 basically states, T plus, T minus and T 0. The single state is up down minus down up, is an antisymmetric state. The triplet state is a symmetric state. If exchange is not going to change the sign here. Okay. So, means spin, when I say spin. Okay. So, triplet as up up down down and up down plus down up. This is the singleton triplet state of 2 dot, that means 2 electrons, 2 dot. Let us look at briefly the singleton triplet states of a single dot. That means you have 2 electrons, but 1 dot. So, the singular state this one state, then triplet state is this. Now, when it's a triplet state means one electron will go to this energy. Singlet means both electrons will be here, but there will be up and down spin state. When the second electron goes here, you can have up up, down down, or down up plus up down. Now, the difference here is the singlet triplet splitting or energy difference in a 2-dot system is very small. That is the main contribution there is. The dots are actually at the same level, then the contribution is only the tunnel coupling between the dot. That is a contribution, which is not a large number. But for a single dot with 2 electrons, the single triplet splitting is large because that is an orbital, that's another orbital state, next orbital. Okay. So, but electron goes to, the second electron need to go to the next orbital. So, this is an appreciable split state. So, the single triplet splitting in a double dot is small, these states are very close by, whereas the single triplet splitting in a single dot is very large. This difference is very, very crucial. This point is very, very crucial to understand certain phenomena such as spin blockade, which is an important tool to read out the spin state. Now, the singlet triplet qubit means you use the singlet and the T0 triplet state. They are very close in energy, but their spins are different. Okay? The spin configuration is different. These two spin states they use to store and manipulate information. So, you have the usual honeycomb charge stability diagram, but you confine your operation to this honeycomb where charge state is 1 1. So, this 1 1 can be in a single state or it can be a triplet state. Okay, single state or this triplet state, that is what you are confining to. So, they are actually not only the spin states are different, but they are also slightly different in charge configurations too. Single state has a skewness in the charge distribution, that means it's more weighted towards one dot, whereas the triplet state is symmetric. Okay. So, this is a very small charge rearrangement, but a sensitive charge detector such as a quantum point contact or a singleton transistor can differentiate these two states. This gives a lot of advantage in 3-dot, because a small difference you can capture means you can distinguish these two states. Okay. Secondly, this is a 2-electron system as opposed to 1-electron system in a LD qubit. Now, if you ask what is the advantage is any decoherence which actually affects both dots the same way. That means a slow, slightly large scale decoherence will rotate the spins. And I said decoherence means it should be a magnetic field or anything which generates a magnetic field or affects the spin state. If they affect both the same way, then both spins will get rotated the same way. So, it is not going to affect the state. That means it is less resilient, it is more resilient and less prone to decoherence which affects both dots, which is a major advantage when you talk about qubits or quantum computation. Secondly, this difference in the charge distribution also will enable you to manipulate and distinguish these two states. But the point here is you need 2 dots, not 1 dot to represent the qubit. Now, let us discuss some simple manipulation of these qubit states. I mean, when I say qubit state, the charge state of the quantum dot, I mean spin state eventually. So, what we are trying to do here is to try to controllably load and unload the state. Okay. This is kind of an important exercise to initialize the qubit state and also detect whether the loading has happened or unloading has happened. So, this is the dot. When you energize these gates, you get a dot in the middle, and this channel here will distinguish whether the electron is the current through this channel will distinguish, the change in the current through this channel will distinguish the electron has loaded or not. Now, we are going to apply pulse to one of the gate which will preferentially or which will address this dot. Imagine that there are many dots, then you can apply this pulse to appropriate gate so that you can change the configuration or you can manipulate the state of the appropriate or individual dots, which is an important criteria for the realization of practical realization of qubits. So now we are going to apply a rectangular wave which is represented by the green line here. And the dot level is part in resonance with the drain, in resonance with the lead. Okay. Now, when you apply a pulse, there is a high state and there is a low state. Low state means is below the, its a pulse is negative with respect to 0, but then during the low state, the dot level will be high because its charge is negative. And positive part, low state let us call it the positive part, high state let us call it, low state let us call it the negative part, unloading part, and high state let us call loading part. Peak to peak is VPP. During the loading cycle, it is a positive part, dot level will be pulled down below the Fermi level. During the unloading part, that is negative side, the dot level will be pushed up above the Fermi level, that is the unloading. The electron can tunnel out, loading time electron can tunnel in. So, this tunnel in or out will be measured by a change in the conductance of the QPC. But the conductance of the QPC is also affected by the direct coupling of the signal to the channel, because these are very small nanoscale devices. So, that also can affect it. So, what that means is you will have the response of this channel, that is how you understand what is happening to the dot, will include both response to the electron tunneling in events in the dot and also response to this pulse. So, you will get both together. So, then you have to understand what is happening to the dot, okay, by decoding the signal. So, this is my signal. So, as a direct response, the current is supposed to follow this path, this dotted green line. But remember, during the unloading time, this drop in signal will change the current, will drop the current also, because this gate is getting negative. So, this current also will reduce because of the cross talk. But that time, remember, the level was up above the Fermi, that will promote, that will basically induce a tunneling out of the electron which is already there in the dot. That will cause a rise in the QPC current because the electron has gone out, it is a less negative charge. So, that means this causes it. So, this time width after you push it out and the rise of the QPC current, that rise corresponds to electron tunneling out. So, that time is the unloading time. You push the level up, but the electron took some time to unload, that is the width. This is the time axis, that is the time taken to unload. Similarly, during the loading, you have pulled the level down, but it will take some time for the electron to tunnel in. Then that will cause a drop in the level in the QPC current, because the positive part of cycle will cause a rise in the current of the QPC, but the electron tunneling in event which happens during that part of the cycle will reduce the QPC current because of the negative charge. What that means is QPC current will go up, but after some time electron will load, then the current will come down. Okay? That is what is happening. So, the time taken after the rise and before the drop is the loading time. That is how much time electron has took to load in, because it will try various times, then it's a stochastic process. So, you take this n number of times and you look at the statistics, what is happening. Okay. So, you can plot this counts, okay, and the time taken to load. Okay. So, what we are seeing here is for two different peak to peak values, we are seeing a rise in the time. For example, lower time get a lower time constant, higher time get a higher loading time, higher voltage you get a higher loading time. Let's try to understand what is happening here. So, remember this pulse is always referred to the Fermi level. So, lower amplitude means the loading time, the level is close to the Fermi level compared to higher amplitude where the level is farther down. VPP is the peak to peak. So, half VPP here for the unloading, half VPP in this case is loading, other half is unloading. So, what happens is when the level is close to the Fermi level, that time the tunnel barrier is thinner, whereas the level is further, the tunnel barrier is thicker, because this is the shape of the well is a parabola. So, lower part of the parabola will see a thicker tunnel barriers compared to the higher part of the parabola. So, here electron will take more time to load in, whereas here electron will take less time to load. Sorry, here electron will take less time to load, whereas here the electron will take more time to load. And when we plot the loading time as a function of the amplitude, you can see that there is a huge enhancement in the time as a function of the amplitude. So, this aspect is called energy selective loading, which is an important point, because you can now preferentially load or unload depending upon the energy. You can choose your pulse amplitude and you can promote or inhibit certain process in the system, and that you can do individually to the dots by choosing the appropriate gate. So, this is a very important aspect and important point, which says these systems can actually are in accord with the diVincenzo criteria, where you can individually address this state and you can individually manipulate the states of the dot. And also you can see that unloading times are always shorter. Okay, unloading part is here. That is because unloading time, the load level is up and the barrier is thinner. Not only there is plenty of states available here to unload. For loading time, there is only one state load and this barrier is thicker. So, unloading times are always shorter. So, you can always the unloading is always assured because it is a fast process. So, you can unload it, initialize state and come back, you can load. If you give enough time, you can make sure it is loaded. Then if it is loaded, then only when you push it unload, you will get this part. If it is not loaded, you will not get this part. So, this is because of the unloading signal. So, that is another way you can make sure that you have loaded the state, you can check it out. Okay. So, what we have discussed now is the two kinds of qubits, that spin qubits, that are realization quantum dots, and some basic idea of how you manipulate the states of the system by using voltage pulses. This also is telling you that you can individually address these qubit states and manipulate it and read out also.